All right, so we are going to do acid bases 2, where we're going to look at strength, pH, and indicators. So strong acids and bases, just know that acids and bases, when we're dealing with them, they have been ionized or dissociated, which means they've been broken up into their two individual parts. So if I've got hydrochloric acid, it's H plus and Cl minus. Now you can find these acids and bases on table K and L. They are listed there for you. Know that most soluble common bases are ionic hydroxides, alkali, and alkaline earth metals. And they are listed, like I said, table L and table K. All right, so we're going to start looking at water because water is unique. Remember, it has the ability to act as both an acid and a base. So when you place water with strong acids, it'll behave like a base. Whereas if you place it with a strong base, it's going to behave like an acid. One water molecule can donate a proton to a different water molecule. You can put water with water, and it will make a base and an acid, right? This is an example of amphoterism. We talked about it briefly in acid bases 1. So water is a huge thing with this, but because of this, we can use this in the equilibrium expression. Now, we didn't go over too much with the equilibrium expression. Just know that it would be the products over the reactants. And in this case, we find that because water is a pure liquid, it can be included in the equation. So water equals H plus OH. With this equilibrium, I can get rid of KEQ with the H2, and I got K of water equals H plus OH, which I can then get rid of K water and just stick with the H plus and OH. These are bracketed because this is ions. We're dealing with acid bases. Here's the biggie. This is why I'm talking about it. H plus and OH equals 1 times 10 to the negative 14th. Okay? Biggie thing. This is what we're going to lead into pH. So this equation is not only applicable to water, but to all aqueous solutions, especially acids and bases. So you've got H2O goes to H plus OH and back. In pure water only, you got your hydrogens equaling your hydroxides. You cannot produce one without the other. So if H plus and OH gives you 1 times 10 to the negative 14th, then based off of that, each hydrogen and each hydroxide has to equal on their own 1 times 10 to the negative 7th, because negative 7 gives you negative 14. Okay, so what does this have to do with anything? Well, when I start to add any acid to that water, it's going to mess with the equilibrium. It's going to put a stress on it. And we talked about those stresses. You got the pressure, you got the temperature, and you got the concentration. We're going to start looking at that concentration because what are you doing? You're adding an acid. And in this, well, for this case, I'm adding an acid. That acid, the Arrhenius acids, they have that H plus, right? So if I add an acid with the H plus into water, I'm actually increasing the amount of H plus on one side. When I increase on one side, it's going to push everything to the opposite. So it'll push back to the water. But by doing that, I'm also going to decrease the amount of hydroxides that's there. Again, the equilibrium shifts to the left and uses the excess hydrogen. Your hydroxides drop. Okay, so when any acid is added, my H plus increases, my OH decreases. But when added together, it is still going to equal 1 times 10 to the negative 14th. That is the concentration. Okay, the acidity or the base. All right, so when NaOH is a base, because it has the OH, when that is added, the OH increases and the H decreases. but we still have 1 times 10 to the negative 14th. Doesn't go away. How can you tell the difference? Well, we're looking at the size, the molarity. Is the molarity of the hydrogen more than the molarity of the hydroxide? Remember our alligator. Alligator eats the most. So in this case, acidic. That means there's more hydronium or hydrogens than hydroxides. Your basics, there's more hydroxides than hydroniums or hydrogens. A neutral means they equal. They're both -7. And when you add them up, they equal -14. This equilibrium is the basis for pH, not POH, pH. Okay, so for convenience, we can use the logarithmic version, mathematically, of concentration to turn a very small concentration of hydrogens into a whole number. So if we know that the pH, or H, is 10 times negative, or 1 times 10 to the negative pH, if my pH is 5, I just have to put that 5 where that pH would be. So my H would actually be 1 times 10 to the negative 5 molarity. And because of that, I can then determine my OH, because my H and my OH have to add up to -14. So -14 minus 5, or 14 minus 5, gives me 9. So my OH has to be -9. There is more H molarity than OH, so the solution has to be acidic. Now, how is that possible? If I take right here and take that decimal and move it over 5 spots this way, it is going to be bigger than when I move this over 9. So it's got to be acidic. One way to remember this is 0 to 6 is acid. 8 to 14 is basic. 7 is neutral. So common household products, you can look at this list right here and look at milk. What is milk? Look at baking soda. What is baking? Look at blood. What is blood? All right, so we're going to look at some exercises. And we're going to indicate if it's neutral, acidic, or basic. So looking at my hydroxides, my hydrogens, it's 1 times 10 to the negative 5th. Okay. My hydroxides is 1 times 10 to the negative 9th. We already talked about this. There's a higher molarity of hydrogen than hydroxide, so the solution has to be acidic. All right, what about this next one? My hydroxides is 10 to the negative 11th. Well, what about my hydrogens? All I have to do is 14 minus 11 to find my hydrogens. So 14 minus 11 is 3. So it's 1 times 10 to the negative 3rd, which is definitely so much bigger than my hydroxides. It's got to be acidic. All right, if my hydroxide is -7, well, 14 minus 7 is 7. My hydrogens got to be -7. It's got to be neutral. It's the same. All right, well, let's look at some lemon juice, something that I drink at night. Usually it helps with my throat and losing my voice every day during allergy season. All right. Lemon juice is 1 times 10 to the negative 4th at room temp molarity. What is the pH? Remember, the pH is just that number right there. Mathematically, how I could do this, I could just do negative log of all of this, and I could get my pH. Or I'm going to make it easy on myself. There's a 4 right there. It's 4. All right. Commonly available window cleaning solution has hydrogen of 1 times 10 to the negative 9th at 25 degrees Celsius. What is the OH? Again, H plus OH gives you 1 times 10 to the negative 14th. Well, if I know H is -9, all I got to do is subtract, and I find that my OH is 10 to the negative 5. Well, -5 is definitely bigger than -9, so it's got to be basic. I did it again. I keep doing this every time I go to this slide. What is the concentration of OH for a solution with a pH of 12? Well, if my pH is 12, 14 minus 12 is 2. 1 times 10 to the negative 2. That is so much bigger than this, which means this substance has to be basic. All right, an aqueous solution has a pH of 1. What are the H and OH? Is the solution acidic or basic? And because I had issues with this, it automatically did it for you. So 14 minus 1 is 13. So my OH has to be 1 times 10 to the negative 13. 1 is so much bigger than negative 13, so solution has to be acidic. Okay, and this just shows you real quick, if I was to do to the negative 1, all I have to do is pop over once, and I got 0.1 molar solution. That's strong compared to negative 13. Okay, so calculate the pH of a 0.010 molar hydrochloric acid solution. Since hydrochloric acid is a strong acid, HCl, I'm looking at just the H's, is 0.001. What do I got to do? Well, I got to move it over. 1, 2, 3. This is going to be 10 to the negative third. There's a negative 3. There's a 3 there. pH is 3. All right, so indicators. I did briefly discuss indicators, saying we're going to look at them. As you can see, indicators can go anywhere, range anywhere from 0 to 12. Yes, they do go up to 14, but we're only going to look to 12 for right now. And you can see all the different colors that you can get to indicate is it acid or is it basic. We have a simplified, a smaller version, table M in our reference table, where you've got methyl orange, I know it's red on one side for acidic and yellow for basic. Bromo blue, yellow to blue. Phenolphthalein, colorless to pink. Litmus, red to blue. Bromocresol, yellow to blue, same with thymol blue. And here's like a universal. It'll show you all the colors going from orange to dark blue, where you can see a couple different sodas and vinegar and ammonia to get the different colors of indicators. All right, based off that, let's look and see if we can answer this example. A solution formed by dissolving an antacid has a pH of 9. Calculate the OH and the H+. Is the solution acidic or basic? What color would the litmus, methyl orange, bromo blue be? All right, let's get down to the H+ and the OH. So H+, I know all I got to do is 1 times 10 to the negative 9. That's the easy part. All I got to do is plug that 9 into the negative part. Okay, now that I got to that, I've got to subtract this from 14. It gives me negative 5. All right, negative 5 is bigger than negative 9, so my solution is basic. All right, what is the litmus going to do with the basic? So for litmus paper, it's going to turn blue. Methyl orange, I believe, is going to be yellow. Bromo blue, it's going to be blue. All right, so acid-basis forms of phenolphthalein. So phenolphthalein, looking at acid, yeah, I'm not sure what this is supposed to be. So any hydrogen with this color, it's going to be a colorless acid. When I add a base to it, add some more water, it's going to tend to turn pink. Bases will turn phenolphthalein pink. If I add acid back, it's going to shift back to white or clear. If I add base, it's going to shift back to pink. I'll go back and forth and back and forth. So the pH scale. The pH scale can be measured quickly, accurately using a pH meter. It is a pair of electrodes connected to a meter capable of measuring small voltage. A voltage, which varies with pH, is generated when the electrodes are placed in the solution. So there's a buffer thing. We're not going to get too much into it. Just know that it does register what the pH should be. All right. What I would like you to work on is acid bases strength and pH indicators. Those are your green pages. Remember, if we didn't go over any of the KEQs, cross it out, you're not doing it. If you have any questions, hope just let me know. Besides that, hope you have a great day.